So I know I'm standing here between all of you and the lunch, so we'll try to finish exactly at the lunch time. So in the morning, I talked more about the big data and the associated deep learning. In this talk, we'll purely focus on the HPC, but at the same time, from the HPC side, like how do we handle the deep learning and in the cloud. Many of you might be familiar here. I mean, the where we are currently towards the Exascale. I mean, this is the #1 system in the world today. That is the Chinese system, MVAPICH2 Lite, around 100 petaflops, and some of the Coral systems are being put together. So we'll see, might be in the June or in the November timeframe. We'll be moving into 200 to 300 petaflops. But the end goal is, of course, the exaflop, and this is where a lot of different countries are trying to compete with each other. So we'll see whether it comes in next year or the following or the 2021. At least by 2020 or 21, we'll have definitely an exaflop system. So I introduced this slide in the morning talk. I mean, so we are seeing a very nice interplay between HPC, deep learning, and the cloud. So what I'll try to focus here, saying what are the kind of things are happening in the traditional HPC domain, and then move into the deep learning, and this is what will be more based on the MPI side. Axel led to that topic earlier, so purely using MPI based kind of things, you can also handle the deep learning very efficiently. And I'll introduce a new problem which is coming up. This is called out-of-core processing. People are going into this deep learning, but sometimes your model is so large that you cannot fit within one GPU's memory. So then how do you handle, how do you scale it to larger ones? So I'll try to show some solution along those lines. It's like just like traditionally in the past we had done out-of-core sort or out-of-core some large applications, similar kind of issues are coming up now, out-of-core DNNs. And then I'll try to finish with cloud for HPC and big data. So this is a very like a parallel programming 101. Many of you must be knowing this is currently the MPI, which is the message passing interface, is based on distributed computing model. Within the node, you see shared memory, which are more like cache coherent. There are some systems where shared memory scales up to reasonable number of nodes, but you cannot scale really cache coherent shared memory to 1 million cores. That is impossible. So that's why this new kind of things which is emerging is the partition global address space. So which tries to provide you a logical shared memory abstraction on top of distributed memory. So you can do get and put from one memory to the other, but the user has to take care of the synchronization. Okay, so that is the model people are seeing to move in the future, and this is getting like more traction. Especially you can provide lightweight one-sided communication at a programming models layer, and that matches with also the RDMA based communication what we see in the network layer. So there is a very good match between put and get at the programming model to the hardware. And the more importantly, this model is easier to express irregular communication. Those of you who have done MPI level programming, you will see MPI is good for regular communication pattern. Like if I am doing a all-to-all, I am doing a reduce, all reduce, stencil, people understand how to handle those. But if you have some application which uses irregular communication, there is a load balancing issues, those kind of things become much more harder to do well in MPI and get the best performance. So that's why like the PGAS models, like people have been working on the language side, also the library side. These are the highlighted ones which are getting more traction in the community. So as we are heading into these kind of programming models, people are also trying to put together hybrid programming models. What it means that it is like taking advantage of both the sides. So I call it like in a diversity, just like any team, you have diverse members and they might have different expertise, how to bring their expertise together. So if you have let's say you have 100,000 lines of code and it is not scaling on a given platform or a given architecture, it doesn't mean that the entire code is bad. It might be that some part of that code is not matching with the underlying architecture, and if I can use an alternate programming model for those subroutines. For example, here if it was a total MPI program, but I see that this kernel and this kernel are not matching with the underlying hardware, and if I can rewrite into PGAS and put them together into a hybrid program, then I can take advantage of both the distributed memory model as well as the PGAS model. And that helps actually to scale the applications. So in that context, if you try to see like how do we design a communication library, this is where in the middle all the programming models come in. And then of course we have the technologies which are below, whether multi-core, many-core systems, networking, and then the accelerators. And this is where we want to deliver the best performance and scalability. Okay? So the challenge for a runtime designer is to take advantage of all the features and mechanisms available here and pass it through some kind of a runtime. So that put into the programming models and that gets translated into some middleware and the application can just call the middleware and get the best advantage. So this is like a layered approach, but you can also do a lot of co-designing across the multiple layers to exploit the best benefit. So these are kind of like if you keep that as a bigger framework and try to ask the question that as we are heading into MPI plus X again people still don't know completely, X could be a simple OpenMP to a PGAS model as we head into the Exascale system. So you will come up with a list like this. These are like any runtime designer, you have to handle million to billion processors. How do you handle efficient inter-node communication? You have to handle a good job startup. There are a lot of issues with collective communication. These are the harder ones to scale, like a broadcast, reduce, all-to-all kind of things. You also need to balance intra-node and inter-node. So these days, the number of cores per node are increasing. So in fact, you will see that many times a lot of communication happens within the node. So how do I optimize those intra-node and then try to also match with the outside, okay? So that I'm not seeing any bottlenecks. You also need to have some good integrated support with GPUs and accelerator, quality of support, hybrid programming, virtualization, energy awareness. So these are all the kind of a wish list kind of things you need to address on. On top of that, I think we are seeing two trends. And the first one is low memory footprint. Okay? So as the system sizes are increasing, if you do a quick math, you will see that the number of cores are increasing in the system. The total amount of memory is increasing, but if you do a quick math, you will see the amount of memory per core is decreasing. Okay? So that puts a big challenge not only on the application developers, but also the runtime developers. Okay? So many times, if you are trying to design like a runtime or an MPI library, I can provide a lot of buffers. I can provide a lot of queues inside the runtime to get a lot of overlap. But then what happens, my memory footprint keeps on increasing. If I tell you that, look, out of the available memory, I'll take 70% of your memory for my MPI library, you will not be happy. Okay? Because as an application, you will only get 30% of the memory. So as the system sizes are increasing, this is becoming very important. And also, as the system sizes are becoming more complex and more features are coming, gradually the field is moving into this kind of a framework I call DLA. Discover, learn and adapt. Okay? It is just like what you see like a normal, let's say driving in a big city, from your home to your work, you always don't take the exactly same route. You make it dynamic decisions based on some accidents have happened, some traffic congestion have happened. Similar kind of things are coming inside the runtime library. Because when you run a job, as many of you know, even though there is a large scale system, I submit like it has 10,000 cores, but I submit a 2,000 core job, I always don't get contiguous allocation. Might be my job is already fragmented on the different parts of the switches. So if I can detect the topology as the job gets launched, I can do a lot of internal decisions like, okay, select this algorithm X versus select the algorithm Y so that I get the best performance. So those kind of challenges are coming, but we need to actually have a very good low overhead techniques so that we can really try to deliver performance, scalability, and also fault tolerance. So these are the kind of challenges any runtime developers are hitting on. So in this context, this is the project I think many of you might be familiar with. This is the MVAPICH project, we started in my group almost the day one of InfiniBand. Prior to that, we were working with Marinette, Quadrix, those kind of systems. So we are going very strong. It is we're celebrating 16 years of this project. We had the very first version of an open source MPI over InfiniBand. It was announced in Supercomputing 2002. Okay, and after that, we are continuously making enhancements. Not only have the basic version, we also have a lot of optimized version. I'll talk a little bit about that. So currently, it's being used by more than 2,800 organizations in 86 countries. And just from our website, we have like crossed 460,000. So in another few months, I think we'll cross the 500,000 mark just from our website. It is also integrated into a lot of other distributions like Red Hat, SUSE, OpenHPC, etc. In addition to the download, as you can see, like this is really empowering a lot of top 500 systems. The number one system in China uses that. Similarly, Oak Forest Packs, Tax Stampede. So like the list goes on. So we have been enabling in this community for the last decade to really get the best performance and scalability from the MPI library. So this is just like a timeline of our all the different releases and the downloads. We're in a very upward curve, as you can see. So this is the broad software architecture. As I said, not only we focus on MPI, but PGAS, also hybrid MPI plus PGAS. We support all the networking technology. We started with InfiniBand, but we support IVAR, Proxy, as well as Omnipath. Here also we support all the different platforms, x86, OpenPOWER, G1, ARM, NVIDIA GPUs, all the platforms we support. I'll show some very detailed numbers. But here, this is where all our new designs come in. How do you design the runtime? So our typical goal, always we try to publish the papers. That is our main objective. But once we have the new designs, we take these designs and then really go through a very rigorous QA testing within our group. We have almost like more than like 100 plus nodes continuously running QA tests 24/7. So we have developed enough capability these days, like if we push a new design or even a new patch, in 36 hours, we can determine whether our design is good or not. Okay, and then if we see some errors, we continuously again enhance those kind of things, and then we post the release. So I'll try to show you some highlights of these designs. First, I'll try to focus on the pure performance aspect on the host side. Then I'll try to bring the GPU side. Then we have done some optimization recently with OpenPOWER with and without NVLink, and also ARM system. And then I'll try to show some application scalability. So these are the kind of numbers. You will see all the different platforms like QDR, FDR, and latest is the EDR. So this is the MPI level. Left-hand side is half round trip, like I send you a ping pong message kind of things, and I divide by 2. So with MVAPICH2, we see around like less than 1 microsecond. 0.98 microsecond is like currently the performance. And then large messages, of course, the bandwidth matters. So we see the EDR is the best numbers here. And then this is the unidirectional bandwidth, the rate at which I can pump data from one node to the other. We get around like 12.5 gigabytes per second. If you do a multiplication by 8, so it's like 100 gigabits. And then the bidirectional is coming to around 200 gigabits. So this is the state of the art commodity networking technologies. So then the question is, that is the basic performance, but that is not sufficient. I mean, you need to take a holistic picture of how the runtime looks like. And the first component we always try to focus on is startup, job startup. So that is becoming a big challenge these days. If you have a 500,000 cores, how do you start the jobs? Okay, and if that takes you like 1 hour, then that is of no good, because every simple jobs you even start, it takes half an hour. So this is where like over the years we have been continuously optimizing it. So these are the very latest numbers. Here if you see, this is a Omnipath system with KNL, Stampede 2, that is as the TAC, Texas Advanced Computing Center. It has the full scale. It has 3,584 KNL nodes, and the number of processes is 230,000 cores. Okay, so if I start an MPI job with 230,000 cores, I can actually finish it in 22 seconds only. The pure, all the jobs are starting to run. Compared to that, if you see other libraries like here, Intel MPI 2018, they start like bending, even starting from 8K, 16K kind of things. Okay. So then here at the right hand side, this is the oak forest packs system in Japan. Similar kind of things here you can see, just in like 5.8 seconds, we are able to do MPI in it. Okay? So we continuously over the last 16 years, we have been enhancing this, not just the basic performance, but also the job startup kind of things. So then as the technology moves ahead, we also try to bring all those things. So this is like a, Mellanox has the new SHARP hardware, where through the hardware they try to do the reduction kind of thing. So we have integrated our MPI stack with that. So this is already available since MVAPICH2-2.3. So you can see here like a HPCG or mini AMR kind of things, you get 12%, 13% improvement using this interface. Now more importantly, it is not just the short messages. Now there is a lot of focus throughout, not only in my talk, in other talks you will see, especially with deep learning, there is a lot of focus on optimizing performance of large messages or medium messages. Okay, so that is also becoming important. So this is where like we have done a lot of optimizations. This was a supercomputing 2017 paper. So here if you see like even a 32 kilobytes all reduce. Okay. This is very important for deep learning applications because a lot of those applications are using those kind of message sizes, not like bytes. They're using kilobytes, megabytes, even sometimes gigabytes. So we need to optimize at that scale. So here you can see like we can give you like almost 2.4x improvement. So this is already available in our MVAPICH2X version. So then more and more of these, like especially looking the deep learning applications into account, I think yesterday you must have heard some talks like you need very good efficient all reduce, all-to-all, broadcast. All these are needed for not just HPC application but also for deep learning applications. So this is a new designs we have been doing called CMA based. It is like a cross memory attach. This is like a, think of like a kernel based communication within the node. Many years back in my group we had introduced something called a LIMIC. So instead of doing a 2 copy, you can handle like a 1 copy approach. And that has become like a default now in the Linux kernel. That's what is the CMA. So if we do an optimized design on this, this was like a last year's IEEE cluster best paper finalist. You can see like we are comparing not only our MVAPICH2, Intel MPI, OpenMPI and the new tune design. This is a log scale. So I can, especially for large messages, we can deliver you like a factor of 3, factor of 4 improvement in performance of this is MPI gather. Similar kind of, this is a very latest design. It has not been incorporated. In fact, we'll be presenting this at the IPDPS conference next month. So this is something based on XPMem. So this is a module which was developed in Sandia National Lab, but that was only for point-to-point. So we have taken that to design collectives, and this is based true zero copy reduction. Okay. So here again you can see like for very large messages, we'll be able to give you like a factor of 2, factor of 4 improvement kind of things. Then moving forward, like those are the kind of the host. We have been continuously working on integrating GPUs. I think some of you might have seen these slides earlier. How many of you are aware of this term, CUDA-aware MPI? Okay, several of you know. So this is the concept, in fact, from my group, we introduced almost 7 years back at the ISC 2010 paper. The first time we said, okay, you can design CUDA-aware MPI library to give very good performance and productivity to the end application. So what does that mean? So typically, if you would have seen like a system like this, if I want to move data from this GPU to GPU, typically most of the time people do a CUDA mem copy, then do an MPI send, and then do another CUDA copy. It is good, very easily you can program, but performance you don't get because you go through a lot of copies. So we asked the question that if you know how to program like an end application person, if you know how to do MPI send, MPI receive from host memory, can you just give the device pointers there? That's all. You don't have to worry about anything. So the end scientist and engineer, they can focus on their domain research, not trying to find out what is happening at the MPI layer, what is happening at the CUDA layer kind of things. And if you just writing like this, everything else, see the animation, it can, MPI library can take care. Okay. So that's what we call like a CUDA-aware MPI. And then if you can do that, then it will really lead to high performance and high productivity. Okay, so that the end scientists can write their applications very quickly, and let the MPI library worry about all the performance, and then you give it the best one. So this is again like we did a 2010-11, we had a series of paper, and after that, like NVIDIA people approached me and saying, okay, why don't we take this design and make it available? So we are working very closely with NVIDIA for the last 6 years with funding. So we take all the very latest from the NVIDIA side and then try to push all the features and mechanisms, and we take advantage of that and then put that into our library. Let me show you the very latest performance. This is the release we made before supercomputing. There is a new release coming out. Look at this number, 1.88 microsecond. We can send data from one GPU over the InfiniBand to the other GPU. Okay, I'm very proud of my team members who did this design. You look at any other library stack in the world, nobody can beat these numbers. Okay, it's the basic InfiniBand, if you host-to-host number is like around 1 microsecond I showed. With another 0.88 microsecond, we are able to send data from a GPU to GPU. Okay, so then with those kind of designs, now you can see like there's an application, Humdi Blue. You can get like a factor of improvement, like a 2x improvement here. And this is our classic showcase. Means all the CSCS folks are here. We are doing, last 3 years, we are doing a very tight collaboration with CSCS and Meteo Swiss. And in fact, we are in Lugano here or throughout the Switzerland. If you see the real-time weather prediction is coming out of this machine, which is sitting on your CSCS there. And we are continuously optimizing the stack. And Meteo Swiss people have been trying to take advantage of that to provide the real-time weather prediction. So we have a very tight collaboration going on between all of you locally here. So then these are the kind of things already available. So these are some of the new things what we have done, especially OpenPOWER. That is the new platform which is coming. So here if you see, we are comparing, these are the intra-node point-to-point. OpenPOWER has a lot of cores, a lot of threads, so we have been continuously optimizing. And here you say 300 nanoseconds. We can do actually MPI communication between the two cores. Intra-socket, similar kind of this latency. This is the large message latency, bandwidth, and bidirectional bandwidth. These are like the internode. This is an EDR system. So here again, we do very similar, except like short messages, we are losing out a little bit. We are improving on that. Otherwise, even we do better than Spectrum MPI, which is a production from IBM and also OpenMPI. We do better. This is the new kind of Coral system, which has the NVLink. We heard about that NVLink and then Pascal. This is on a Power 8 system. We are working on the Power 9, which is the Sierra machine which is being deployed. So here if you see intra-node, we are able to give you at an NVLink 33.2 gigabytes per second bandwidth. Okay? So at an MPI level, we are able to take care of the pure, the full NVLink bandwidth kind of thing. And these are all available in the latest MVAPICH2-GDR stack. So you can just still download and then get these kind of numbers. So now we are taking all these collectives, as I introduced earlier, like the CMN collectives. These are not available yet. That's why we call MVAPICH2-GDR next. It will be coming out soon. So now if you take those kind of new designs, so this is like an intranode reduce and all to all, compared to Spectrum MPI and all, you can see factor of improvements we can give you. Even this is for 4K, medium message sizes, this is for large message sizes. We can give you a lot of benefits here. This is the new XBMM design. I indicated earlier, like on the host side, if I take it to the OpenPOWER platform, similar kind of things, I can give you like a factor of 2, factor of 4. So these are on the pipeline. These releases will be coming out soon. Then we are also working very closely with ARM. That is the new platform which is coming up. So here again, you can see this is publicly available. ARM cores are a little bit slower. So here, that's why this is the intranode. It's around 740 nanoseconds. Okay, so we can do MPI latency within the core, and you get very good performance on the ARM. So then, if you compare, like these are some of the application numbers. So as many of you know, like any MPI library these days has 300 to 400 parameters. Okay, you can tune based on your architecture, based on your platform. So we are taking a lot of effort from our group and also from the community. So we have created best practice session or a best practice page on our MVAPICH project site, so people have been contributing there. So we want to help the community so that you don't waste similar amount of time. If somebody has tuned it, you can exactly use the similar number. So this is trying to show it's like a the standard spec MPI. A lot of people do the evaluation. So here you can compare with Intel MPI. We can deliver you like a across the board performance improvement. This is on Skylake with Omnipath. Similar kind of things. For some application, even we can give you 38% benefit. These are really large scale numbers. These are run with on the TAG Stampede. So you can see like this is the MiniFE, Neuron, Cloverleaf, and it goes like these are the Skylake numbers. These are the KNL numbers. You can also do comparison because TAG has two partitions. One is a Skylake and then another is the KNL. And we are able to steadily grow here up to 8,000 cores. This is 760, but this is a 3,000 cores. So all these numbers are actually available. You can see like if you go to the website, exactly you will find out like which parameters to change. Okay, because these are very customized kind of things. Any MPI stack has so many parameters. You need to adjust them to get the best performance. So that's what we have done. So if you take a look at this link, here you will see like a lot of people have contributed, and we are soliciting contributions. So if you have run some application with MVAPICH2 and see the best performance, please feel free to contribute that, and we'll provide you acknowledgement on that side so that the entire community gets benefited. So this is a new initiative we have started in the last year. So now then moving forward, I'll quickly see what is happening at the deep learning side purely from HPC. So there are two broad challenges are taking place. One is a scale up. That means within the node, like I put more and more GPUs, how do I get the best performance? And then I have the scale out, the distributed training kind of things. So a lot of solutions are being put here, and starting from not only the pure like the Nickel 2, Hadoop, gRPC, MPI. So we are also trying to provide some kind of a co-designs also. I'll illustrate that quickly. And I think some of the earlier talks, even Axel also led to this. One of the common collective which is used in most of the deep learning, distributed deep learning, is all reduce. Okay, so if you can deliver all reduce with good performance, you will see all your deep learning applications will get. So we have been continuously optimizing, and a lot of alternative solutions are being provided. Like there is a one Baidu all reduce, or let's say OpenMPI has something. So we have done. This is like our optimization. These are already available in our public version. So you can see compared to all these solutions, we can across the board for all different message sizes, we can give you very good benefits. This is with the Nickel 2. I think Axel led to that. This version has not been released. It's coming up. So you can say compared to even the Nickel 2 from NVIDIA, we are able to pure MPI-based solution for small messages, large messages, we can do better. This is for broadcast. This is for reduce, similar kind of story. And then this is for all reduce. Okay. So you don't need to be in any other library. If you have an MPI library installed, you should be able to do your deep learning applications very well. So that's the kind of message I'm trying to give. So you don't need any other library here. Now, in addition to that, I think many of you might be when you are talking to the deep learning people, and I think I had a brief discussion with Axel. He can relate to this. A lot of deep learning people don't know much about HPC. Okay. You need to tell them a lot of things, like whatever we have learned in the HPC field for last 20 years, how do you access data, how do you distribute data. So they don't do these kind of things very well. So here what we have done is we have taken similar kind of things into Caffe. Caffe is one of the framework. So we have done a co-design so that instead of doing very dumb way, doing some broadcast or reduce, all reduce, we can make some changes in the Caffe layer itself and then link it to our layer. And then that leads to very good scalability to up to 128 GPUs. So this is like we have a OSU Caffe. We have a project called High DL, High Performance DL. So you can just download here and then run it on your system. You will be getting similar kind of performance. So then one more thing, I hinted this is a newer problem which is coming out you know the GPUs have some limited memory. Depending on your GPUs, it could be 16 gigabytes or 32 gigabytes, but the DL peoples are going for bigger and bigger models. So if the model doesn't fit within your GPUs, then the question is, how do I proceed? So this is like an out-of-core deep learning problem, you can think. Just like the previously in many old days, it used to be out-of-core sorting. How do you handle? Your physical memory is not good enough. So here we have taken like the unified memory. I think Axel introduced that. So we have used that unified memory concept, and we have an out-of-core Caffe. And using these kind of things, you can also simplify the design. Like we have a out-of-core Caffe which eliminates almost 3,000 lines of code, 3,000 lines of code. And then it tries to deliver good performance. So here if you see like this side is trainable, this is out of core, okay? So for example, for a larger model, you cannot run here, but this is the green one, which is our best design. You can give very good performance. And a lot of people are saying, okay, if your GPU doesn't fit, how about doing it on the host? Okay, that is a fallback kind of thing somebody can do. So we are just comparing it with an Intel Caffe and Intel Caffe optimized, whatever the public version there. There could be a lot of optimization there. We can compare whenever that version become public. But the whole idea is that now we have a way to move forward so that we can also do like a out-of-core deployment. And then finally, the virtualization, and I think I hinted this in the previous talk. How do we take advantage of all these designs and try to run it on the cloud? So here we have like continuous support. We have been doing with OpenStack, Docker, Singularity. The main challenge here is that how do I detect the topology? How do I know who is talking to whom? Those kind of concepts are not there in the traditional container environment. You just have VMs, they are just running. So to illustrate the point, if you think there are like 3 bars, so this is the bar which is the basic MVAPICH2. It will run in a virtualized environment, there are no issues, but it may not give you the best performance. But whereas this one, on a bare metal without virtualization, so that is the best you can achieve. Okay, so if you compare the difference between this green and the gray, there is a performance gap. But this is the orange one is our new design. So when we take a lot of topology information into account, if a VM moves from another node to my node, we can quickly detect that, look, these 2 VMs are sitting on the same node. I can do a lot of shared memory communication, not go over the network. So if I do like this, I can bring this gap, performance gap, like a 1%, 2% kind of things. Okay, so this is already available in our specialized MVAPICH2 version. Similar kind of things. We have provided support with Singularity. This got a Best Student Paper Award at the UCC conference. And also the same, our MVAPICH2 GPU version, so now it is containerized. So you can actually take it, I think you indicated the NVIDIA, the cloud initiative, so it exactly matches. You can now take it and without any performance sacrifice, you can run it in the container environment. So with this, let me conclude here. So I just outlined the kind of things what we are doing, what are the new, but continuously we are trying to push, as this project is like 16 years, we are aiming forward. Our next objective is to really deliver performance on these 10 million core kind of systems. And these are some of the new things we are working. MPI plus task, that is a kind of a new paradigm which is coming. Tag matching hardware for Mellanox, adapter memory, we are working on this. KNL has this MCDRAM. So how do you take that MCDRAM inside the MPI library? How do you take advantage of that? Similarly, trying to optimize on NVLink and Caffe. And then, of course, the continuous support on the deep learning. So that is the new field which are coming. The more and more we know, the communication patterns we are trying to optimize. So these are the kind of things what will be released out. So with this, let me again thank all our sponsors and all my heroes who do all the hard work. And I'll be happy to take questions if you have any quick questions. Otherwise, over the lunch or afternoon, we can talk.